Okay, then let's start with the practical application. So if you have looked at the code here in the shader toy, let me just give the link just in case somebody doesn't have it. So if you go to common and to this estimator here, you have an algorithm that gives you the light energy arriving from some path. So it generates a path, hopefully it hits a light source, and then it returns you the color that you get after evaluating that. And the algorithm, it looks something like you can have a one-to-one correspondence to what I've described here. So you have a variable that's throughput, which is initialized to 1. So this is it really describes the attenuation of your energy. So the more bounces you have, the smaller this would be in general, if those bounces are not mirror, so the less light can travel along this path. And at the sensor, that starts with as 1, and at the sensor, the contribution to the flux. So what you want to measure, so we want to measure the flux at a single pixel, is 0. So the first thing to do would be to generate a point on the sensor. So you have a camera, you have the film of the camera in your virtual world, and some subset, let's say some rectangle on that film is your pixel, corresponds to your pixel. So you want to integrate over that area. So the first thing would be to generate a point X inside that pixel, given a let's say random number that's in 0, 1, the square. And you have a transformation to go from here to here, and we'll see what the transformation is up in the theory. But at the very least in the code that you see, here if you go to buffer C, at the very beginning, here you have a loop where you accumulate samples, and here you generate the random number that I talked about. You add it to your screen coordinates to get some other coordinates, and then you generate an array that passes through this. So you have a transformation that maps it to the virtual world, and you can find the mapping in the function generate ray, which gives you basically the direction based on the point on the pixel that you pick. So this is really your transformation. Let's continue. So that's the first thing. You generate some point inside a pixel. The second point is to generate a direction. Now, if your camera has a non-zero aperture, so not a single point, then you want to generate a point in there, and from that construct a direction. But in our case, we have a pinhole camera, so there's only one possible direction that the ray can pass through. So we pick that specific direction. So we don't need to sample more for that. And then we enter a loop where we want to evaluate, okay, what's the contribution of that path? And let's look at the implementation of this. So that would be estimator path tracing, Lambertian. So this thing corresponds to this thing. And you can see that we go over several bounces. So we say the maximum allowed bounces are B, and we iterate over that. Now, if we run out of bounces, so if our iteration index k is greater than b, then just return the what you have accumulated. In the very beginning, this is simply black. So first, here we have array defined by x and psi. We intersect the scene with that. We find some intersection point. If there is no intersection point, we set some flag that says, okay, there is no intersection point. We set the outgoing direction, so towards our sensor, as theta, which is the opposite of psi, so just negate it. So the direction along which light travels, in some sense, is theta, and c is the direction along which importance travels. Then when we intersect a surface, the surface has a normal that faces either outwards or inside it, but we always want the normal that faces uh, if you look at our ray of the scattering direction, we want it to match the normal. Let's look at the normals also. So if you use space in this code, you can visualize the normals. So you always want to have the correctly facing normals. And for example, I can enter this bow and still get the correct normal. That's what the flip of the sign does there for the so this thing that you see here. So this is just an implementation detail to get the correctly facing normal for bounces, etc. Now, after that, we if we hit an emissive object, we can add its emission, so the radiance multiplied by the throughput, but at the very beginning, the attenuation is simply 1, so this doesn't change the emission, and you add this to the color. Let's look at the implementation with that regard. So if you don't intersect anything, as we mentioned, then it says, okay, we are done. But before that, maybe the background has some radiance, and the background here does have some radiance, so we can add that. Let's look at the just the direct illumination, for example. So this thing, now you can see the only light source that is directly illuminating it is the background in this case. And in the case of the cornel box scene, I have the light source and I have the background. So both act as light sources. So the background acts as a light source if I intersect nothing, and this light source here, if I intersect it, it acts as a light source. Yeah. So we have this in the code. The flux is this the color. So we are adding the throughput multiplied by some modulating factor, and here I sample a texture cube map to get the radiance. So this really corresponds to what you see here. And that's in the case that you intersected nothing. So this code here is if you intersected nothing. Now similarly, if you intersected something, then you can simply add the radiance, the emitted radiance of that something. So this light here, for example, multiplied by the throughput. So it's the exact same thing as mentioned. If there's no intersection, then we just return the color that we have accumulated already. Now the next thing that we want to do is we want to scatter our ray for the next bounce. We pick a random point in 0, 1 squared, so square. From that random point, we generate a direction, a scattering direction. So this is a mapping that gives you that direction, let's say on the upper hemisphere, and we compute the density of that. We also need to evaluate the BRDF, the cosine, dividing by the density, multiplied by the throughput, and update the new throughput. So this is really the attenuation that occurs at this very bounce. And we can see that in the code. So here's the generation of the random point. Here's the mapping. So this is psi, this dir is psi, which is cosine weighted. We have a cosine weighted mapping here, so it's given a normal and it's given the random point and it returns you psi. We also have the throughput evaluation. Since everything's a Lambertian in the scene, this is just a constant, so just the color multiplied by pi. Pi comes from the density, and the cosine from the rendering equation cancels from the cosine from the density of the mapping. Finally, at the very end, we want to continue bouncing our ray, so we prepare the origin of the next ray, which is the intersection, plus some offset along the normal, so we do not self-intersect in the next bounce. And we continue with the scattered direction of the ray. And you can see it here. Again, we update the origin of the ray and we continue with the new psi. Questions on that? This is the basic algorithm. The whole I guess, material today is to show, okay, how do you get from the theory to that, and then to discuss what can you do extra. So because that's a simple estimator, you can also make other estimators and then combine those with multiple importance sampling. Any questions on this?
I have a quick question.
Yeah.
Can you remind us how the throughput is related to, maybe, if I'm not sure to be correct, but is it the throughput, is it related to the importance, or is it something else?
The throughput, it's in here, it contains parts of the rendering equation, as you can see, divided by the density of the mapping that you used to go from 0, 1 to, let's say, uniformly distributed or cosine distributed points on the sphere, on the unit upper hemisphere, let's say. So with every bounce, you grow this t with more terms. Does that make sense?
Okay.
And we
yes,
will
okay.
see.
So this is not the importance. So this is just. I try to find
it's throughput.
A human.
It's exactly throughput. And so you can think of it as an attenuation factor. So it tells you how much light can, let's say, can travel along that path. And as you can see, the light gets multiplied by this. And with more bounces, usually this decreases and decreases and decreases. And what, for example, Russian roulette does is says, okay, if this is too small, well, don't waste time computing anymore, just cut it off. Other questions?
Yeah.
Okay, if there are no questions, I guess we can start with the theory. So going backwards. Yeah, I guess yeah, it probably makes sense to start from here then. And so just as a reminder, what we saw in the previous chapters was radiometric quantities were introduced. As we saw here, we will be computing the flux for each pixel. Also, if the camera is a pinhole camera, actually you're computing the radiosity. If the camera is an orthographic camera, then you're computing the intensity per sensor, and obviously you have the radiance and spectral radiance as some kind of fundamental quantities here. We also saw that the BSDF is used to describe the behavior of your surfaces in terms of light interaction. So the material, really, the BSDF gives you the material. We also saw how the scene is described. So it's just a set of points, M, and at every point we have a defined normal. So if I have a point X, this is the normal at this point. We also can introduce lights in the scene. So LE would be non-zero for those, but for every other surface, for every other point, we'll say, okay, LE is simply zero, so that's not a light source. And finally, we have the sensors as mentioned. So for every pixel, let's say for a pixel G, you have the emitted importance function, which is 1 over the sensor and 0 everywhere else. Or if you want to add some sensitivity of your sensor, so let's say it's more or less sensitive to light, then you can make this not be 1, for example 20 or cosine theta or something like that to get various sensitivity effects of your camera sensor. And with these things, so with these definitions and this, if those are defined, it's enough for us to compute the final image. We also saw that, okay, if we have the radiance function, the unknown radiance function, so this is known, this is unknown, we can write the solution in terms of an integral operator, a sum of those integral operators that goes to infinity. So it's an expansion of the rendering equation. You can, in some sense, recursively expand it until you get this sum. We also saw in chapter 3 what to do about, because these are integrals, what to do about these integrals. Well, if we have an integral over an arbitrary domain omega, and let's say with respect to whatever measure, if we can find a mapping from the unit hypercube to this domain, so in here this mapping is T, and the density of this mapping is P, and the density was simply the Jacobian of the inverse mapping, then we can approximate it numerically, because we can, for example, take a sequence of random points in this interval here, in this unit hypercube, and just write the estimator of that. So it's just an average. So we know how to solve these integrals. We know what these integrals look like through these. So we actually have everything that we want. The final thing is, okay, we actually want to compute the flux at every pixel. So we have an inner product, which is simply two integrals over the pixel sensor and the aperture sensor, in the aperture of the emitted importance. So where the where you have the sensor, so that's 1. Where the sensor is not, it is 0. And the radians that, okay, we know how to expand. So we expand it here, but the inner product is linear, so we can take out the sum and you get an infinite sum of these terms. So this is the measurement equation solution for this specific sensor. Questions? Okay, if there are no questions, let's continue on how to solve that, and we will start with the very first term, so k0, where this is t to the power of 0, so this is simply LE, to see what this inner product looks like. So, right, okay, let's before that, let's discuss the problem of this infinity here. So we see, okay, we have an infinite sum of increasingly dimensional integrals, but obviously in a computer you cannot go to infinity. So what we'll do is we'll stop earlier, so stop at some bounce B and go no further. What's the idea behind that? Well, the idea is that if we choose B well, then everything after that would be, the error after that would be too small. Let's see, do I have it here? I think I do. Okay, so for example, this is the first this is the 0th bounce, first, second, third, and you see the energy decreases. So let's say if you stop at the 5th, the energy would be so small that it would be almost invisible. And I can show you the same thing in my code here. So this is, again, the 0th bounce. We can go to the first one, let's say, with this. So this is only energy coming from 1 bounce away. We can go further, 2 bounces away, energy coming only from 2 bounces away. So this, and you see, okay, the energy decreases further. Now we can say, okay, 3 bounces, even smaller energy, it's almost invisible. And if you add this up, it's so at around 5 bounces for these scenes, the energy is so small that it doesn't make sense to waste more computation there. So we just cut it off and we say, okay, if the error is small enough, it's totally fine. And I mean, at some point, the precision with which you can represent colors, so the quantization levels that your screen can represent, your error, if it's smaller than that, well, you can't even see it. So it makes sense to cut this off in practice to some finite b. Now, when is this an issue? Imagine that you have mirrors that can bounce almost infinitely many times without getting attenuated. Then this is an issue. And in general scenes, you have more or less specular surfaces, and then you have also diffuse surfaces. So you want to keep B fairly large for such scenes, but you do not want to continue on paths that get darker faster. So let's say diffuse paths. And what people do in that case is adaptive path termination, also known as Russian roulette. So if the path is too dark, just don't waste resources on it anymore and do another path. Yeah. What about the estimators? Okay, as mentioned, we will use either random points, or for example, low discrepancy, etc. sequences. And if you want to generate a random point that is in the unit hypercube, d-dimensional unit hypercube, you can simply pick d points in 0, 1, and then stack them in a vector. And that's again uniformly random point. The first estimator that we will consider is the zero bounce estimator. So that's the very first term, which looks like this after you expand it, let's say in the area formulation. So WE is one only for points that are on the sensor. So this is the sensor, our rectangle of the pic corresponding to the pixel, and directions through which the ray can pass. So only through the pinhole camera in our case, for instance. So this is 0 for everything except these two sets. So we can rewrite this as equal to that, or in the solid angle formulation as this. So you can see that this inner product is simply an integration over the pixel and an integration over the directions from which light can arrive at that pixel. Finally, we can take that and we can write an estimator for it if we have a mapping from 0, 1 squared to the sensor, and if we have a mapping from 0, 1 squared to the directions that we care about, or if we have a pinhole camera, this mapping is unnecessary. And we have the densities with respect to this mapping here and here. So this is our estimator. How do we evaluate such an estimator? Well, first, how do we evaluate this LE? We can use the fact that radiance arriving at x from direction CI is the same as the radiance leaving this point intersected along this direction in the opposite, assuming there's vacuum, obviously. And this we can check in our renderer, so we can trace a ray, intersect something, and check the radiance there. So that's how you compute that term. The cosine term is fairly obvious. So you at the point you care about, you check the normal, you multiply by the direction that you picked, you dot the two, so that's a dot product. The two are unit length, so you get the cosine, and we will see what the densities look like a little later. Yeah, so this is simply the arriving light at your film. Now you can see a cosine term here, and what it would imply in practice is that directions that are further away from the center of the film, or pixels that are further away, are darker, and that's an effect known as vignetting, and you can see it here. So it's something that happens in cameras. How you can avoid this effect is by simply taking, for example, making your sensors here more sensitive and here less sensitive, so it's the same brightness everywhere. So that's one possible solution. We will also see that 3 cosine terms go into the numerator from this density here. So actually the vignetting effect is a cosine to the power of 4. And what you can usually do is say, okay, I will take this WE term, rather than being 1 and 0, have 1 over cosine 4, then we can cancel out these terms, and we won't have such a brightness diminishing effect. Obviously, if you want the effect, you can keep it. You don't have to cancel it out. So it really depends on what you choose for your sensor sensitivity function. Yeah, as mentioned. So if we write the equation and we say, okay, this is 1 over cosine power 4, then this gets cancelled and this gets cancelled. I think we can do a break if there are no questions. Are there questions?
Yes, I have one actually. In your shader example,
Yeah.
Are you actually accounting for the vignetting effect?
Yes. Actually, so here's the trick. So the trick is that if you do not add any terms, if you just pretend the where is that? If you pretend that the probability density function here and this here do not exist, so if you don't add them, it's like you set WE to 1 over cosine to the power of 4. Do you get it?
That's because the density is actually cosine weighted, or am
Yeah,
I wrong?
because from here you get a cosine to the power of 3 in the numerator, and this is 1 cosine again.
Oh,
We will see it
no,
down
right.
below. So you get a cosine power of 4. But if you cancel that and you pretend, okay, it didn't exist to begin with, so you canceled it, and you just wrote an estimator, that's, where is that?
No, I got it.
If you just write an estimator that looks something like that, which is what people usually do, but they don't know why they do it, then it's like you said, okay, I made my sensor to be inversely proportional to 1 over cosine power 4, and that's why these terms disappeared. So that's the trick. So actually,
Okay.
what we
That I
use
didn't
already takes into account uh, the how to remove the vignetting.
know. Okay.
Other questions? Okay, if there are no questions, I'll take a 5-minute break and I'll be back in 9:32 my time. So yeah, see you later. Okay, I'm back. Can you hear me?
Clear.
Okay. Yes, so where was I at? Yes, so I was talking about vignetting, and if you click on the link here, wait, does everybody have the PDF? I think I linked it somewhere at the, yeah, it's here. So if you click on the link here, that would lead you to a, let's say, a longer discussion of how exactly this happens and where the cosine term, cosine to the power 4 term comes from. And there's also a reference about this with respect to actual cameras, so that you can see, okay, you actually have this in the real world. So the fact that you don't have vignetting in your photos, etc., is because the camera compensates for that effect. So either through the lens or through the sensitivity, but in our case, we just say, okay, we can choose our sensitivity be whatever we want, so we can remove this effect if we want to. Yeah. In the term here, we saw that we can also write it in terms of the through the geometry term, through the area formulation, and just as a reminder, you have the geometry term here, and once again you can compensate for vignetting by turning your WE into 1 over a cosine to the power 4, etc. Yes, so we saw two mappings. One maps to the pixel and the other maps to the aperture. The one to the pixel should be fairly easy to deal with. So you take the corner of your pixel, let's say V, you take one edge of the pixel, so these are vectors, another edge of the pixels, and you simply multiply by one random number here, one edge, the other, and you get some random point inside your pixel. If you assume your pixel is a, let's say, a rectangle or whatever. And then the density of this is simply the size of the pixel. So this gives you the area. So this is a cross product. And then you take the length. Yeah, so that's a pretty trivial mapping, and you can see it in the code. It should be in generate ray. Yeah, so you can see it here. So that's instead of a corner here, we take the center of the pixel. Then we take, I've transformed this to be between -1 and 1. So we start from the center and we can pick a point inside the pixel. And this is a vector to the right, and this is a vector to the up and down. And the UV are computed in buffer C, so you can see them here based on the pixel coordinates. Yeah, so that's how we choose a ray direction, and that was also available in the algorithm here. So you can see, okay, here we choose the point on the pixel, and here we choose the point on the aperture, but in our setting, at least in the code, it's a pinhole camera, so the second choice is unnecessary. I mean, you always pick the pinhole, so the only point through which light can pass. So we discussed that. So these are the mappings. The aperture mapping is quite a bit more involved. So if you have an aperture, not just a pinhole, then you need to pick a point on it, and then you need to transform it to a solid angle formulation by having a factor like this here. Then if you assume, so this is, you don't have to go into such details, I'm just recounting what this section talks about. So you get a term like that. Now if you assume that the aperture A is parallel to the film, you can derive some things that tell you, okay, you get one cosine from that, and then you get one cosine from the length squared part. So 2 cosines from there, so you get at the end of the day, you have a cosine to the power of 3, so what I mentioned, but also in the numerator, you have distance squared from the film to the aperture. And ideally, if you don't want this to affect the brightness of your image, get vignetting or whatever, then you say, okay, I choose my sensitivity function, WE, to cancel out this term, so to cancel out this density here, and to cancel out the cosine. So if you do that, then the brightness won't change. Now this, as mentioned, the first density for picking the pixel, it's 1 over the area. So the larger your pixels, the brighter your image would become. Now you may not want that because you don't want your brightness to change with the resolution. So what you can do is you can also put that in WE. So you can cancel this out and cancel the size of the aperture. In the real world though, if you have a larger aperture, so more light can arrive from it, obviously your image would be brighter. But if you don't want to have such brightness changes just from making your aperture larger or whatever, then you can say, okay, I pick my sensitivity so my brightness doesn't change with the size of the aperture, with the size of the pixels, and with the location of the pixels, so the cosines here. Then you're left with an estimator that looks like this, and what you actually see in the code. As you see, for example, in the algorithm here, as you see in the algorithm, we never change the throughput for the primary race. So the throughput here is 1. If we actually didn't have this WE term that cancels out stuff, then you would multiply the throughput by the cosine to the power of 4, also divided by the distance squared, and then also by the size of the pixel and the size of the aperture. And then this would be something else. So it won't be just a 1 here. So it's only because we say, okay, we want a sensor sensitivity that cancels out these terms, so brightness doesn't change. So everything's nice. That's why we get such a simple estimator. Is that clear? Questions on it? No questions, then I guess it's clear that, okay, this would simply be an average of the incoming ray. So you just pick random points on your pixels and you should trace and see, okay, do I hit anything or not? And if you hit something, well, it would be bright. If you hit nothing, then it would be totally black, and you can see that here. So where is it? If we only care about light arriving through 0 bounces, so this estimator, well, here you can see that the background radiates light, and in this example, the background radiates some light, and you also have emitted light from the lamp. So that's with 0 bounces, exactly the estimator that we were looking at. So this thing. Yeah, here I've also provided a mapping that you can use. If your aperture is, you assume it to be a disk, then you can use that, and you can transform your points there. If you want to, for example, produce a depth of field effect, then you have to use that instead of simply a pinhole camera. Also, you can be more creative and choose, like, say, an aperture that's based on an image, say a teapot. Then the aperture would be in the form of a teapot, so from where light can arrive. And if you have, let's say, something very blurry and very bright, you would actually see this shape of the teapot. What else? Yeah, if you have a pinhole camera, as mentioned, you do not pick points on the aperture. There's only one valid point, the pinhole point. And if you have an orthographic camera, then your directions are simply perpendicular to your film. Finally, you want to estimate many pixels, so not only one sensor. So you estimate one sensor, then you compute a second and third, etc. And if you use the same sequence for all pixels, then you get correlation artifacts, structured artifacts, which show up as aliasing. Now, if instead you say, okay, I randomize the sequences between the pixels, then you usually get the error as white noise. Finally, if you can do that, you should try to make your error be correlated as blue noise, so look like blue noise. Then it is visually optimal with respect to the human visual system, and also optimal with respect to denoiser. So you would need a smaller filter to remove the error. Questions? Okay, if there are no questions, let's continue with the one bounce estimator. So that's after the first bounce, what happens? Well, again, we expand this notation. It's almost the same thing as before, but here we have an operator, and we can expand that too using what we have for the operator from the rendering equation. So this expand to that. We can also rewrite it in a solid angle form. And now we will have to write an estimator for this whole thing. So these two terms would be for the integration of this integration of the pixel, this over the integration of directions of your aperture, and this is for the bounce. So S squared here is the unit sphere of directions. What's the estimator like? Well, it is this. So you may recognize this from the zero bounce estimator, but without the LE. And the new part, the BRDF multiplied by the absolute value of the cosine multiplied by LE, but arriving from one bounce away. And divided by the density here of picking a scattering direction. This is an absolute value in case, for example, you choose a BRDF or BSDF that transmits light, because then this needs to be positive, obviously. So here you pick the point on the pixel the exact same way as for the zero bounce estimator. Same thing for the aperture point. The only difference is how do you pick the point for the scattering. One possibility is just pick a random direction on the upper hemisphere around the normal. Then you have this CI2. The other option is to pick a point on the scene, or a point, let's say, on a light source, so xi2. So what you see here. And these two, so this formulation is simply the solid angle formulation, and this formulation is the area formulation. Now, I have assumed that we have picked WE to cancel out these terms, so I don't have to deal with that. So that's why you see only these parts, just for simplicity. Obviously, you can keep this, and you can have vignetting, etc., if you want to. So you have two estimators. One is a solid angle estimator, the other is a area estimator, so that you would use that one, for example, for direct light sampling. Yeah, so how do you map from 0, 1 squared to the upper hemisphere? The easiest thing to do to get a, let's say, cosine weighted density is to pick a random point on the unit sphere, offset it by the normal, and normalize, and that would give you a direction that is cosine weighted. And you can prove that. I've given the mapping to the unit sphere here. You can use it to generate the point on the unit sphere given two random numbers. Yeah, where does this happen in my code, for example? Let's see. It's in here. And if you search that, let's see. So you can see the mapping to the unit sphere, and then the mapping to the cosine weighted, simply as mentioned, the normal plus a point map to the unit sphere, and you can normalize if you want to. It's not necessarily because the directions are equivalent regardless whether they're normalized. Yes, so that's how you would generate your directions C2. Yes, so what happens if you use such a density, a cosine density? Well, then you can see it here. It will cancel out the cosine, and we know that the density is normalized by a factor pi, so you would get an estimator like that, where the cosine is missing. Now, if you instead are able to produce a density that is proportional to the BSDF, then the BSDF would get cancelled from the density in the denominator, and you would get something like that. Now, if you can produce a mapping that has a density which is the product of the BSDF and the cosine, then both would cancel, and you would have a very, very simple estimator like that. So this estimator here would generally be better than, let's say, this one, because you've cancelled out some terms that can produce a higher error. So for example, if I were to pick 16 samples and use that, and 16 samples and use that, then the error, you should assume the error usually would be lower here. Questions?
In this case, I mean, this last one you just showed, the source of variance will be the emitted radiance from bouncing away, right?
Yes, exactly. So for example, I shoot a ray, but I don't hit a light. Well, I just wasted the sample, right?
Okay. Is there this could be really a perfect example, maybe the best above all worlds, possible worlds, but would it be possible to actually also not only sample the BRDF and this cosine term, but also cancel some radiance terms in this case? Is there any sort of kind of
yeah, there is. Theoretically, you can construct a, if you know the solution, if you know the solution, then you can construct a sampler which you give it one sample, exactly one sample, and it gives you the exact solution. But you need to know the solution. Now, obviously, in practice, you cannot do that, but people are smart, and what they've done is, for example, path guiding, which approximates the product. So the whole product here, it approximates it, and it gets something close enough, and it samples with respect to it. So then then you even cancel out some part of LE, let's say, and some part of this and some part of that. So people have tried to do that, but the optimal thing is you need to know the solution to actually do it. If you don't know the solution, you can use some approximation. So here you use, obviously, analytical integration techniques to, let's say, get rid of that or get rid of that. Now, path guiding is an approximation of what you have. And then, yes, then it would be close to constant. So it would be a very good estimator that you just need to give it a few samples and the error decreases very much. Does that answer your question?
Okay, that's good. Let's answer it. Thank you.
Okay. And yeah, in terms of best of both worlds, well, a cheap solution is to just say, okay, I have an estimator that looks like that, and then I have a direct light sampling estimator, and I combine both with multiple importance sampling to say, okay, I try to be good where one is good and be good where the other is good. So try to use the better one. Is what multiple importance sampling does. Yeah, so the other option, so what's the other option? The other option is this estimator here, which is with respect to the area formulation, and which you can use to sample lights. So you pick a point on a light, and then you use the estimator mentioned, and then you get an estimator that doesn't miss the light. Obviously, the light may be occluded, in which case you get a miss again. But imagine you have a very, very small light. Then the probability of hitting it by just sampling the upper hemisphere is low. But the probability of hitting it, if there is no occlusion with respect to this estimator, is 100%. So that's a good estimator if you have small lights, bright small lights. If you have multiple lights, you can, for example, L lights, you can pick a light with a probability 1 over L, or you can set all the probabilities, for example, depending on how bright the light is or how large it is. Usually flux is used. And then multiply this probability that you picked with the density of picking a point on it. So that would be the final density that you see here. So it would be the density of the probability of picking a light multiplied by the probability of picking a point on that light is this probability. Yeah, so how do you evaluate that? I already explained how LE is evaluated. The visibility term, you simply create a line segment between x1 and x2, but you offset them a little bit along the normals so you don't self-intersect. And you check, okay, do I intersect anything from the scene in that line segment? And if I intersect something, I can stop early and say, okay, this is 0, then no contribution. But if I intersect nothing, then this is 1 and the light actually arrives. And the geometric terms was also discussed. Yeah, as mentioned, the benefits are that, okay, you can, for example, very small light sources where the probability from just shooting randomly rays in the upper hemisphere is low. Now here the probability may be 100% in that case. But on the other hand, well, you do not take care of this term. You do not take care of this term, which also adds a distance term and another cosine term and also this term. So you do pay something for that. And as mentioned, you could try to combine the two with multiple importance sampling to take care of, let's say, both problems at the same time in a reasonable manner. Questions? No questions? Then let's go to the key bounce estimator, and it looks pretty nasty, but honestly it's just the one bounce estimator applied k times. And you see that in here, you just have a product of what you had in the, so if you had only that in the one bounce estimator, well, here you just have a k product of it, of k segments along the path. And then the estimator is simply this product, once again divided by the density at each bounce, and you end up at a light source. Or equivalently in the area formulation, same thing. Also, so this is only solid angle and this is only area formulation. What you can do is you can mix and match. So you can some bounces can be solid angle and some bounces may be area formulation. What's usually done in practice is you do the first bounces using a solid angle sampling or BSDF sampling, whatever, and then at the very last vertex you just connect to the light source directly so you don't miss it. And you can combine this. What people usually use multiple importance sampling for is they combine this estimator that connects directly to the light source at the last bounce with the estimator that may hit a light source just off randomly. So you sample a light ray and then you intersect the light source and then you can add the contribution. Otherwise, if you don't use multiple importance sampling, well, you cannot add the contribution there. You would only be able to add contribution that arrives from this if you use that estimator. Yeah, questions? Okay, then let's continue with the more practical part. We saw how to write the k-bounce estimator, so in solid angle form. That was it. Let's also look at the k+1 bounce estimator, and you can see they are very similar. In fact, we can take this part here, this whole part, and for conciseness call it tk. So this is the product. And then we can write the two estimators very concisely. This should say k+1. Yeah, I'll fix it. And then we can find a relationship between the two. So tk+1, for one more bounce, we just have to multiply by the BSDF of that bounce, the cosine, and divided by the density. So we can construct our path iteratively, starting one bounce at a time, and at every bounce just multiply the throughput by the BSDF, the cosine, and divided by the density. Now, if you assume that, okay, at every dimension we use the exact same number of samples, then we can interchange some sums. So what the flux looked like was a sum over the bounces over the estimators. And each estimator was an average for each dimension. Now what you can do is you can swap the sums and then it's an average of paths. So you can start from the sensor, reach a light source over however many bounces. So this is 0 bounces plus 1 bounce energy plus 2 bounce energies, etc. Take this whole thing and then divide it, sum your samples up and divide them. So just to get an average of paths. And it's the same thing as mentioned. And that's how we get to the algorithm. So the throughput that you saw, for example, the update here, well, it's really this update here. And you can see it from these two estimators, and notably from the expansion of the equation. Yeah, so if you take, let's say, tk plus 1, then you see, okay, it's just a multiplication by the BSDF, the cosine, and divided by the density, which is exactly what you see in the algorithm. And it is exactly what you see also in the code. Let's show that. So again, BSDF, Lambertian, from the density, and the cosines cancel out because in the density you have a cosine in the denominator, and you have a cosine from the rendering equation in the numerator. So this is really the update that you see right here. Questions? Then let's wrap this up with multiple importance sampling. As mentioned, there is an estimator that can use direct light sampling at the last vertex, and you can combine this with the solid angle one. And you can do this through multiple importance sampling, something we mentioned in chapter 3. The only thing you have to be careful about is that the density should be with respect to the same measure. So for example, if we have the density for picking a point on the light, so this density here, we want to transform it with respect to the solid angle measure, and you can do so using this equation. Then you can construct the weights for the solid angle and for the light source sampling, and the only difference that you see in this is, okay, here in the throughput you also multiply by when you add the flux, you also multiply by a weight. So that's really it. Yeah, I think this concludes it. Questions on that? Okay, if there are no questions, I guess I could tell you what the next chapter is about. It's about radiosity. It's not a mandatory chapter in the sense that nothing after that really relies heavily on that, on radiosity. So if you're not interested, so you can look through it. If you're not interested, you can skip it. Also, even in the meeting, I won't go into the details that they go. For radiosity, I'll mostly cover the theory. In chapter 7, we will have bidirectional path tracing, and I'll try to prepare code before that with multiple importance sampling and with obviously with the direct light estimator that we saw in the theory here. So where is that? Not this, not that. Yeah, so that one. And then we'll mix the two with multiple importance sampling in the, so it would be an extension of the current code. Yeah, I think this concludes it. So thank you for the attention. If there are no questions, feel free to go.
Thanks.
Thank you, Krieger.
Thank you.
Thanks.
Thank you.